Deep within the dark caves of South Africa, researchers uncovered the remains of a mysterious ancient species, Homo Naledi. Unlike other early humans, they lived far from sunlight, navigating narrow passages and hidden chambers. This discovery challenges everything we thought we knew about our distant relatives. Chapter 1. Cave Discovery. You know what's strange about human evolution? We spend so much time looking for missing links and grand narratives, but sometimes the most mind-bending discoveries come from the most unlikely places. In September 2013, two recreational cavers named Rick Hunter and Stephen Tucker were squeezing through the cramped passages of the Rising Star cave system in South Africa, part of the famous cradle of humankind. They weren't looking for fossils. They were just exploring. But when Tucker squeezed through a narrow vertical chute, we were talking about gaps just 20 centimeters wide, the width of a sheet of paper turned sideways. He found himself in a chamber 30 meters underground. The floor was literally carpeted with bones. Human-like bones, everywhere. What they had stumbled upon would become the largest single collection of ancient human relatives ever discovered in Africa. More than 1,550 fossil specimens from at least 15 individuals, ranging from infants to elderly adults. But here's what makes this discovery so extraordinary. These weren't just any ancient human relatives. They were something completely new, something that would challenge everything scientists thought they knew about human evolution. The cave system itself tells part of the story. Rising Star Cave, also known historically as Westminster or Empire Cave, sits in the Malmani Dolomites of the Blauwbank River Valley, about 800 meters southwest of the famous Swartkrans site. The cave has been known to recreational cavers since the 1960s, with its passages mapped and explored by the Speleological Exploration Club for decades. But the chamber where Hunter and Tucker made their discovery, which would later be named the Naledi Chamber, meaning Chamber of Stars in Sotho, had remained hidden. Getting to this chamber isn't easy. Today, only 48 humans have ever been documented as entering the Naledi Chamber. You have to navigate through a section called Superman's Crawl, where most people can only fit by holding one arm tightly against their body and extending the other forward, inching through spaces just 25 centimeters high. Then comes the vertical chute, a 12-meter descent through gaps barely wider than your shoulders. When Tucker's photos reached paleontologist Lee Berger at the University of the Witwatersrand on October 1, 2013, Berger knew immediately that something unprecedented had been found. The sheer number of bones visible in the images was staggering. But there was something else that struck him as significant. The arrangement of bones and even some survey pegs suggested that someone had been there before, decades earlier. Berger quickly assembled a team for what would become known as the Rising Star Expedition. But there was a unique challenge. The cave's extremely narrow passages meant that only small-bodied team members could access the site. Berger put out a call for skinny scientists, early career researchers who could physically fit through the cave's restrictive openings, and had the expertise to conduct a proper excavation in such challenging conditions. The team that descended into the Naledi Chamber in late 2013 and early 2014 was unlike any fossil expedition before it. Working in near-total darkness in cramped conditions where they could barely move, these researchers carefully documented and extracted fossil after fossil. What they brought to the surface would revolutionize our understanding of what it means to be human. By the time the initial excavation concluded, the team had recovered an unprecedented treasure trove of fossils. But the real surprises were yet to come. When they began analyzing what they had found, they realized they were looking at something that didn't fit any existing category of human ancestor. The skull was too modern for the body. The hands were too advanced for the brain size. The feet were perfectly suited for walking upright, but the shoulders and curved fingers suggested a life still partially spent in trees. The discovery team faced a fundamental question. What exactly had they found? The bones clearly belonged to the human genus Homo, but they possessed a bewildering mixture of primitive and advanced features. Some characteristics looked like those of much older human ancestors from 2 million years ago. Others seemed remarkably modern. It was as if evolution had mixed and matched features across vast stretches of time. In 2015, Berger and his team announced their findings to the world. They had discovered a new species of human ancestor, which they named Homo Naledi, Naledi meaning star in Sotho, honoring both the cave where they were found and the stellar team that discovered them. But even as they celebrated this remarkable find, many questions remained unanswered. How old were these fossils? How did so many individuals end up in such an inaccessible cave chamber? And what could these strange human relatives tell us about our own evolutionary story? The mystery of Homo Naledi was just beginning to unfold. What scientists would discover over the following years would challenge fundamental assumptions about intelligence, behavior, and what makes us uniquely human. But first, they needed to understand exactly what they were looking at. Chapter 2: Species Description. When scientists first examined the Homo Naledi fossils in detail, they encountered something truly puzzling. Here was a species that seemed to have been assembled from spare parts spanning millions of years of human evolution. The holotype specimen, designated DH1, comprising a male's partial skull, upper jaw, and nearly complete lower jaw, immediately revealed the contradictions that would define this species. Picture an adult Homo Naledi standing next to you. They would come up to about your shoulder, roughly 143.6 centimeters tall, or 4 feet 9 inches. At 39.7 kilograms, they would weigh about 88 pounds, making them notably smaller than most modern humans, but larger than earlier human ancestors like the Australopithecines. Their body mass fell somewhere in between, suggesting an evolutionary position that was equally intermediate. The most striking feature would be their head. The Homo Naledi skull displays a fascinating blend of ancient and modern characteristics. From the front, you'd notice a well-developed brow ridge stretching across their forehead, similar to what you might see in Homo erectus or even the much earlier Homo habilis. A pronounced ridge, called the supraorbital torus, would create a distinctly archaic appearance. Yet the overall shape of the skull, while small, would seem surprisingly modern compared to much older human ancestors. But it's the brain that tells the most surprising story. Inside that skull sat a brain of only 465 to 610 cubic centimeters, roughly 1/3 the size of a modern human brain. To put this in perspective, that is only slightly larger than a chimpanzee's brain, and well within the range of the much more ancient Australopithecines. The encephalization quotient, a measure of brain size relative to body size, was just 4.5, smaller than virtually all other members of our genus. Yet remarkably, detailed studies of brain impressions left on the inside of Homo Naledi skulls revealed something unexpected. Despite its small size, the brain showed structural similarities to other Homo species rather than to earlier hominins or great apes. The frontal lobe, in particular, displayed features associated with more advanced cognitive abilities. Areas of the brain linked to tool use, social behavior, and even language showed human-like development patterns. Moving down from the head, the contradictions continued. The teeth of Homo Naledi were relatively small and simple, more like those of modern humans than the large, heavily built teeth of earlier species like Paranthropus robustus. They lacked many of the accessory cusps and complex features seen in more primitive hominins. The molars increased in size from front to back, a primitive characteristic. But overall, the dental pattern suggested a diet that didn't require heavy chewing or processing. Interestingly, almost half of the teeth showed chips and fractures on the enamel surface. This wasn't random damage. The pattern suggested these individuals regularly consumed hard, abrasive foods, possibly underground tubers covered in grit and dirt. The frequency of dental chipping was remarkable. 44% of teeth showed damage, higher than any other fossil human species studied. Only modern baboons, which consume large quantities of underground plant foods, showed similar patterns. The body of Homo Naledi told an equally complex story. The shoulders were configured much like those of Australopithecines, positioned in a way that would have facilitated climbing. The rib cage was relatively broad, similar to the 3.2 million-year-old Lucy specimen of Australopithecus afarensis. The pelvis showed a flared shape reminiscent of much earlier human ancestors. But then there were the hands. The hands of Homo Naledi were remarkably human-like in their overall proportions and capabilities. The wrists, thumbs, and fingertips all showed adaptations for precise manipulation and tool use, virtually identical to those of modern humans and Neanderthals. Yet the finger bones themselves were distinctly curved, even more curved than those of Australopithecus, suggesting adaptations for climbing and grasping branches. The contradiction was striking. Hands perfectly designed for making and using tools, attached to arms and shoulders, better suited for life in the trees. It was as if evolution had equipped Homo Naledi for both terrestrial tool use and arboreal living simultaneously. The lower body presented its own surprises. The legs were long and slender, more like those of modern humans than earlier hominins. The femur showed features associated with efficient long-distance walking. The foot and ankle were particularly human-like in their configuration, suggesting that Homo Naledi walked with a fully upright, efficient gait very similar to our own. Yet even here, primitive features persisted. The pelvis retained characteristics that would have made childbirth more difficult than in modern humans. The overall body plan suggested an individual capable of efficient bipedal locomotion, but still retaining significant climbing abilities. Sexual dimorphism in Homo Naledi was relatively limited, more like modern humans than earlier species, where males were often dramatically larger than females. This suggested social structures that might have been less dominated by physical competition between males. The vertebral column, where preserved, showed proportions similar to other Homo species, though the specimens were among the smallest recorded for any hominin. The neural canals were proportionally large, similar to modern humans and Neanderthals, suggesting a well-developed nervous system despite the small overall body size. One of the most remarkable aspects of the Homo Naledi discovery was the completeness of the fossil sample. With more than 1,550 specimens representing at least 15 individuals across age groups from infants to elderly adults, scientists had access to a comprehensive view of the species' anatomy. This wasn't just a few isolated bones or a single skeleton, it was an entire population preserved in one location. The age distribution of the individuals was particularly noteworthy. The presence of both very young and very old individuals, along with adults of various ages, suggested that whatever brought these people to the cave wasn't a single catastrophic event. Instead, it pointed to some process that occurred repeatedly over time. What emerged from all these anatomical details was a picture of a species unlike any other in the human fossil record. Homo Naledi possessed a mosaic of features that spanned millions of years of evolution, combined in ways that seemed almost impossible. They had hands capable of sophisticated tool use, but brains smaller than any other Homo species. They walked upright with modern efficiency, but retained climbing adaptations more pronounced than their ancient ancestors. This anatomical paradox would become central to understanding not just what Homo Naledi was, but what their existence meant for our understanding of human evolution itself. Here was a species that challenged the linear progression models that had dominated paleoanthropology for decades. Evolution, it seemed, was far more creative and unpredictable than anyone had imagined. Chapter 3. Dating revelations. When Lieberger and his team first announced the discovery of Homo Naledi in 2015, they faced a significant problem. They had no idea how old these fossils were. The bones had been found in a cave chamber with no other animal remains, no stone tools, and no clear geological context that would allow for easy dating. For 2 years, the age of Homo Naledi remained one of the biggest mysteries in paleoanthropology. Many scientists, looking at the small brain size and primitive anatomical features, assumed these fossils must be ancient, perhaps 2 million years old or more. After all, no hominin with such a small brain had been found from more recent time periods in Africa. The mixture of primitive and advanced features suggested these might be very early members of the genus Homo, perhaps contemporary with species like Homo habilis or Homo erectus. But in 2017, the scientific world was stunned when the dating results were finally published. Using multiple independent dating techniques, researchers determined that Homo naledi lived between 335,000 and 236,000 years ago, firmly in the Middle Pleistocene, not the distant past that everyone had expected. The dating process itself was a masterpiece of scientific detective work. The team employed several different methods to cross-check their results. They used electron spin resonance, ESR, dating on 3 teeth, which measures radiation damage in tooth enamel accumulated over time. They applied uranium-thorium dating to cave formations called flowstones, sheet-like deposits of calcite that form where water flows down cave walls and floors. They also used optically stimulated luminescence dating on sediments, which measures how long mineral grains have been buried in darkness. All these independent methods converged on the same shocking conclusion. Homo naledi was not an ancient relic from the dawn of our genus, but a contemporary of early modern humans. These small-brained hominins were living in Africa at the same time that Homo sapiens was beginning to spread across the continent and beyond. This revelation fundamentally changed how scientists had to think about Homo naledi. The minimum age of 236,000 years meant that this species was alive well into the time period when anatomically modern humans were already present in Africa. The maximum age of 335,000 years placed them in the Middle Pleistocene alongside other large-brained human species like early Homo sapiens and late Homo heidelbergensis. The implications were staggering. Here was a species with a brain only slightly larger than chimpanzees, persisting in Africa hundreds of thousands of years after much larger-brained humans had already evolved. This challenged the long-held assumption that bigger brains automatically conferred evolutionary advantages that would drive smaller-brained species to extinction. The young age also made the anatomical contradictions of Homo naledi even more puzzling. How could a species with such primitive features survive for so long alongside more advanced human species? What ecological niche were they occupying that allowed them to persist when conventional wisdom suggested they should have been outcompeted long before? The dating results forced scientists to reconsider some fundamental assumptions about human evolution. The traditional view had been that evolution proceeded in a relatively linear fashion, with primitive species being replaced by more advanced ones in a steady progression toward modern humans. But Homo naledi suggested that the reality was far more complex, with multiple human species coexisting for extended periods. This wasn't entirely unprecedented. On the Indonesian island of Flores, the diminutive Homo floresiensis had survived until roughly 50,000 years ago, overlapping with modern humans. But Flores was an isolated island where unique evolutionary pressures might explain the persistence of an archaic species. Homo naledi, by contrast, lived in mainland Africa, the evolutionary heartland where most major developments in human evolution had taken place. The young age of Homo naledi also raised intriguing questions about their relationship with contemporary species. Were they in contact with early modern humans? Did they compete for resources, or did they occupy different ecological niches that allowed them to coexist? The absence of stone tools in the cave chambers where Homo naledi was found made these questions even more complex. Some researchers suggested that the young age actually supported the idea that Homo Naledi might have been responsible for some of the stone tool industries found in southern Africa during this time period. The early and Middle Stone Age archaeological record from the region showed sophisticated tool-making traditions, but few fossils had been found in direct association with these tools. If Homo Naledi was the only identified human species living in the region during this period, perhaps they were the toolmakers after all. This possibility was both exciting and problematic. The hands of Homo Naledi certainly showed all the anatomical features necessary for sophisticated tool manufacture and use. The precision grip, the robust thumbs, the wrist joint configuration, all suggested individuals fully capable of making stone tools. But if they were making tools, why weren't any found in the cave chambers where their bones were discovered? The dating also had implications for understanding the evolutionary origins of Homo Naledi. If they were truly as young as the evidence suggested, then either they had evolved relatively recently from a more archaic ancestor, or they represented a relict population, a species that had branched off much earlier but somehow managed to persist largely unchanged for hundreds of thousands of years. The relict hypothesis gained some support when researchers considered that the fossil record from this time period in southern Africa was relatively sparse. It was possible that Homo Naledi had been living in the region for much longer than the dated fossils indicated, but had simply not been preserved or discovered in older deposits. Alternatively, some scientists proposed that Homo Naledi might have evolved from a more recent ancestor, perhaps through a process of evolutionary reversal, where some features became more primitive over time. This was a more controversial idea, as it required explaining how and why a large-brained ancestor might have evolved into a smaller-brained descendant. The dating results also highlighted the remarkable fact that the Middle Pleistocene was a time of unprecedented human diversity. Rather than a simple progression from primitive to advanced, the fossil record now showed multiple human species with very different characteristics living at the same time. Homo Naledi, with their small brains but sophisticated hands, represented just one point on a complex spectrum of human variation. This diversity raised questions about what drove human evolution during this crucial period. Traditional models had emphasized the advantages of larger brains, more sophisticated tools, and greater behavioral complexity. But the persistence of Homo Naledi suggested that these weren't the only viable evolutionary strategies. Perhaps there were multiple ways to be successfully human in the Middle Pleistocene. The young age of Homo Naledi also made their cave context more intriguing. If these individuals had lived recently enough to potentially encounter modern humans, then the question of how they ended up in such inaccessible cave chambers became even more complex. Was this evidence of sophisticated behavior by a small-brained species? Or were there other explanations for the accumulation of bones in the rising star caves? As scientists grappled with these questions, one thing became clear. Homo Naledi had fundamentally changed our understanding of human evolution. The simple progression from primitive to advanced that had dominated thinking for decades was no longer tenable. Instead, the human story was revealed to be one of remarkable diversity, with multiple species experimenting with different evolutionary strategies across vast stretches of time. The dating of Homo Naledi marked a turning point in paleoanthropology. It demonstrated that even 250,000 years ago, being human could mean many different things. The future would bring even more surprising discoveries about what these small-brained relatives were capable of. Chapter 4: Underground Mysteries. The question that haunted researchers from the moment Rick Hunter and Stephen Tucker first photographed the bone-littered floor of the Naledi chamber was deceptively simple. How did at least 15 individuals of Homo Naledi end up in one of the most inaccessible places on Earth? To understand the magnitude of this mystery, you need to appreciate just how difficult it is to reach the chamber where these fossils were found. The Naledi chamber sits approximately 80 meters from any known entrance to the Rising Star cave system. The journey there requires navigating through a series of increasingly challenging passages, culminating in the notorious Superman's Crawl, a section where even small-bodied individuals must hold one arm against their body and extend the other forward, inching through spaces barely 25 centimeters high. After Superman's Crawl comes the Dragon's Back, another narrow passage, followed by a vertical chute dubbed the Chute, a 12-meter descent through gaps that narrow to less than 20 centimeters wide. Modern cavers, equipped with sophisticated lighting, protective gear, and detailed maps of the cave system, find this journey challenging and risky. For individuals without modern equipment, it would have been extraordinarily dangerous, if not impossible. The chamber itself provides no evidence that anyone ever lived there. There are no signs of habitation, no hearths, no tools, no food remains, no evidence of any daily activities. The bones appear to be the only large vertebrate remains in the chamber, which is unusual for cave sites that typically accumulate diverse animal remains over time through various natural processes. When the research team first began analyzing the taphonomy, the study of how bones end up where they refound, they systematically evaluated every possible natural explanation for the accumulation. Could water have carried the bones into the chamber? Detailed geological analysis revealed no evidence of water flow into or out of the chamber that could account for transporting complete skeletons over such distances through such restrictive passages. Could predators have dragged the bodies into the cave? The bones showed no evidence of carnivore tooth marks, scavenging damage, or the kind of random scattering typical of predator accumulations. Moreover, no large predators would have been capable of navigating the narrow passages that lead to the chamber, especially while carrying human-sized bodies. Could the bones have been washed into the chamber by flooding? Again, the evidence argued against this explanation. The chamber shows no signs of having been subject to water flow, and bones transported by water typically show characteristic damage and sorting patterns that were absent from the Homo Naledi remains. Could natural cave-ins or geological processes explain the accumulation? The geological team found no evidence for catastrophic events that could have trapped multiple individuals over time. The chamber appears to have maintained its current configuration throughout the period when the bones were deposited. Could the individuals have accidentally fallen into the chamber? The configuration of passages makes this extremely unlikely. There are no vertical shafts leading directly to the chamber that someone could have fallen down. The complex navigation required to reach the chamber argues against accidental entry. One by one, every conventional explanation for natural bone accumulation was eliminated. This left researchers facing an unprecedented possibility. Perhaps these bodies had been deliberately placed in the chamber by other Homo Naledi individuals. The idea of intentional body disposal by Homo Naledi was revolutionary and controversial. Such behavior had previously been attributed only to large-brained species like Neanderthals and modern humans. The concept that a species with a brain, roughly one-third the size of ours, might engage in complex mortuary behavior challenged fundamental assumptions about the relationship between brain size and behavioral sophistication. But the evidence was compelling. The presence of both complete and partial skeletons in various states of articulation suggested that bodies had been placed in the chamber while still held together by soft tissues, then gradually decomposed in place. Some elements were found in anatomical position: a nearly complete foot and ankle, a partial hand and wrist, ribs and jawbones in sequence, indicating that complete bodies had been deposited rather than individual bones being scattered into the chamber. The age distribution of the individuals was also significant. The chamber contained the remains of infants, juveniles, and adults of various ages, including elderly individuals. This pattern is consistent with repeated mortuary behavior over time rather than a single catastrophic event. If the accumulation had resulted from accident, disease, or natural disaster, you would expect to see a more random age distribution or a bias toward particular age groups. Perhaps most remarkably, in 2017, researchers discovered a second accumulation of Homo Naledi remains in another chamber of the Rising Star cave system. The Naledi chamber, located more than 100 meters away from the Naledi chamber with no direct underground connection, contained the remains of at least 3 more individuals, including a well-preserved adult male skeleton and a juvenile. The discovery of a second, completely separate accumulation of Homo Naledi remains in an equally inaccessible part of the cave system, strongly supported the hypothesis of intentional placement. The statistical probability of 2 separate accidental accumulations of the same species in such unlikely locations was effectively 0. If Homo Naledi was indeed deliberately placing their dead in these cave chambers, the implications were staggering. Such behavior would require several sophisticated cognitive abilities: the ability to navigate complex underground spaces, the physical and social coordination to transport bodies through extremely challenging terrain, the cultural transmission of knowledge about where and how to conduct these activities, and some form of group cooperation to carry out such physically demanding tasks. The behavior would also have required what researchers call deferred gratification, the ability to invest significant time and energy in activities that provide no immediate benefit. Carrying a body through the treacherous passages to reach these chambers would have been exhausting. Dangerous work with no obvious reward other than the completion of the mortuary act itself. Some researchers suggested that the body disposal might have served practical purposes, removing decaying corpses from living areas to prevent scavengers or disease. But the enormous effort required to reach these particular chambers seemed far out of proportion to any practical benefit, especially when much more accessible caves or surface locations would have served the same hygienic purposes. Others proposed that the chambers might have held special significance for Homo Naledi communities. Perhaps these dark, hidden spaces represented something like sacred places, locations set apart from the world of the living for the disposition of the dead. This interpretation would suggest that Homo Naledi possessed some form of symbolic thinking about death and appropriate treatment of the deceased. The controversy surrounding these interpretations reflected deeper tensions in paleoanthropology about what kinds of behaviors could be attributed to small-brained hominins. Many researchers remain skeptical that a species with such limited cranial capacity could engage in the kind of complex, coordinated behavior that intentional burial would require. Critics pointed out that the cave system might have been more accessible in the past, with entrances that have since been sealed by geological processes. They suggested that what appeared to be difficult access today might not reflect the situation hundreds of thousands of years ago when Homo Naledi was alive. Others argued that the research team hadn't adequately explored all possible natural explanations for the bone accumulations. Perhaps some combination of geological, hydrological, and biological processes could account for the remains without invoking complex behavior by Homo Naledi. The debate highlighted a fundamental challenge in interpreting archaeological and paleontological evidence. How do you prove intentional behavior from the fossil record? Unlike stone tools, which clearly represent deliberate manufacture, the absence of natural explanations for bone accumulation doesn't automatically prove human agency. Yet as research continued, the evidence for intentional placement continued to accumulate. The discovery of articulated skeletal elements, the absence of other animal remains, the repeated pattern in 2 separate chambers, and the consistent elimination of natural explanations all pointed toward the same remarkable conclusion. If Homo Naledi was indeed engaging in mortuary behavior, it would represent the earliest evidence for such complex treatment of the dead in the human lineage. More importantly, it would demonstrate that sophisticated cultural behavior was independent on large brain size. that even our small-brained relatives were capable of activities that we had thought were uniquely human. The mystery of how Homo Naledi ended up in the rising star caves opened a window into the cognitive and cultural capabilities of our early relatives. But this was just the beginning of the surprises that these caves would reveal. Chapter 5. Diet Analysis. One of the most revealing windows into the daily life of Homo Naledi comes from an unexpected source: their teeth. When researchers examined the dental remains from the rising star caves, they discovered a story written in chips, fractures, and wear patterns that painted a vivid picture of what these ancient humans ate and how they lived. The first thing that struck researchers was the sheer frequency of dental damage. Among the Homo Naledi specimens, an extraordinary 44% of teeth showed evidence of chipping or fracturing that had occurred during life. This wasn't damage from fossilization or excavation. These were injuries that the individuals had sustained while alive, then continued to live with for months or years afterward. To put this in perspective, only about 21% of teeth in Australopithecus africanus show similar damage, and just 13% in Paranthropus robustus, two species that scientists have long suspected ate hard, tough foods. Among living great apes, the figures are even lower, around 11% for gorillas and only 5% for chimpanzees. Even modern human populations, known for consuming particularly harsh diets, rarely exceed 25% dental chipping. The only living species that showed comparable levels of dental damage were baboons, where about 25% of teeth displayed fractures. This comparison was particularly intriguing because baboons are known for their heavy reliance on underground plant foods, tubers, roots, and rhizomes that they dig up with their hands and consume without cleaning off the attached soil and grit. The pattern of damage in Homo Naledi teeth provided additional clues about their diet. The chips were predominantly small and located on the chewing surfaces and between teeth, rather than on the front edges where you might expect to see damage from using teeth as tools. This suggested that the damage resulted from chewing hard or gritty foods, rather than from cultural behaviors like food processing or tool use with the teeth. Many of the damaged teeth showed multiple small chips, sometimes 5 or more on a single tooth, which was virtually unique among the comparative samples researchers studied. This pattern of repeated minor damage suggested that whatever was causing the chipping was a regular part of the Homo Naledi diet, not an occasional hazard. When researchers examined the microscopic wear patterns on Homo Naledi teeth using advanced dental topography analysis, they found further evidence for a unique dietary adaptation. The teeth were smaller than those of Australopithecus and Paranthropus species, but they were higher crowned and showed greater resistance to wear. This combination suggested that while Homo Naledi wasn't processing foods that required massive chewing muscles like some earlier hominins, they were dealing with foods that contained more abrasive particles. The dental evidence pointed toward a diet rich in underground storage organs, tubers, roots, and other plant parts that grow beneath the soil surface. These foods would have been nutritious and energy-rich, providing excellent caloric return for the effort invested in obtaining them. But they would also have been covered in soil particles, grit, and other abrasive materials that would cause exactly the kind of dental damage seen in Homo Naledi. Underground plant foods require specific strategies to obtain. Unlike fruits or leaves that can be simply picked from trees, tubers and roots must be dug up, often from significant depths. This would have required tools. Even simple digging sticks would have been essential for efficiently accessing buried food resources. The sophisticated hand anatomy of Homo Naledi, with its human-like precision grip and robust thumbs, would have been perfectly suited for making and using such tools. The emphasis on underground foods also made sense in the context of Homo Naledi's body size and energetic needs. As a species with relatively large brains for their body size, even though small compared to later humans, they would have had high metabolic demands. Underground storage organs are among the most energy-dense plant foods available, making them an excellent choice for meeting these elevated caloric requirements. But the dental evidence revealed something even more specific about Homo naledi's feeding behavior. The pattern of wear and damage suggested they were consuming these underground foods with minimal processing, essentially eating them raw, dirt and all. This contrasted sharply with modern human populations, which typically clean root vegetables thoroughly before consumption, or with other hominin species that showed evidence for more extensive food processing. This raw consumption of gritty plant foods had profound implications for understanding Homo naledi as technological capabilities and cultural practices. While their hand anatomy suggested they were fully capable of making sophisticated stone tools, the dental evidence indicated they weren't using such tools to process their food extensively before eating. Either they lacked certain food processing technologies, or they chose not to use them for reasons that aren't immediately apparent. The teeth also provided evidence about the seasonal and geographic patterns of Homo naledi subsistence. The consistency of dental damage across individuals of different ages and from different areas of the cave suggested that underground plant foods formed a reliable, year-round dietary staple rather than a seasonal fallback resource. This indicated that Homo naledi had developed a specialized adaptation to this particular ecological niche. Interestingly, the dental morphology of Homo naledi was quite different from that of other Homo species living around the same time period. While early Homo sapiens and late Homo heidelbergensis showed dental patterns consistent with more varied diets, including significant amounts of meat, Homo naledi seemed to have specialized in a more plant-focused subsistence strategy. This dietary specialization might help explain how Homo naledi managed to coexist with larger-brained human species for hundreds of thousands of years. By focusing on underground plant resources that required specific extraction techniques and tolerance for gritty, unprocessed foods, they may have occupied an ecological niche that wasn't directly competitive with other human species. The emphasis on underground foods also had implications for Homo naledi's ranging patterns and territorial behavior. Plants that store energy in underground organs are often distributed in patchy, seasonal concentrations. Exploiting these resources effectively would have required detailed knowledge of local environments, including when and where different species would be producing their underground storage organs. This knowledge would have been particularly important in the South African environment where Homo naledi lived. The region's Mediterranean-like climate, with wet winters and dry summers, would have created seasonal cycles in plant productivity. Underground storage organs would have been most available and nutritious at certain times of year, requiring Homo naledi groups to time their movements and activities around these natural cycles. The dental evidence also suggested that Homo naledi possessed the cultural knowledge necessary to identify and process underground plant resources. Many underground storage organs are difficult to distinguish from poisonous plants when viewed only from their above-ground parts. Successfully exploiting these resources would have required sophisticated knowledge of plant identification, seasonal timing, and proper processing techniques, all of which would have been transmitted culturally from generation to generation. Some researchers suggested that the heavy reliance on underground plant foods might also explain certain aspects of Homo naledi's anatomy beyond just their teeth. Their robust ham bones and curved fingers might have been adaptations not just for climbing, but also for the repetitive digging motions required to extract underground foods. Their relatively small body size would have reduced overall caloric requirements, while still allowing for the energetic demands of extensive foraging activities. The dietary evidence from Homo naledi teeth painted a picture of a species that had developed a highly specialized ecological strategy. Rather than competing directly with larger-brained relatives for the same resources, they had carved out their own niche focused on underground plant foods. This specialization may have been key to their long-term survival in an increasingly crowded landscape of human species. Yet questions remained about other aspects of their diet. While the dental evidence strongly supported heavy reliance on underground plant foods, it couldn't tell the complete story. The presence of burned animal bones in some areas of the Rising Star cave system suggested that Homo Naledi might have occasionally consumed meat, though whether they were hunting, scavenging, or simply sharing cave space with other species remained unclear. The dental analysis had revealed a species that lived very differently from their contemporaries, with a dietary strategy that was both sophisticated and specialized. But as researchers would discover, their unusual diet was just one piece of a much larger puzzle about how these small-brained humans lived in their complex world. Chapter 6. Anatomical Paradox. The skeleton of Homo Naledi presents one of the most perplexing puzzles in human evolution. How could a single species possess such a bewildering mixture of primitive and advanced features? When researchers first began detailed anatomical studies of the Rising Star fossils, they found themselves looking at what seemed like a chimera, a creature assembled from parts spanning millions of years of evolutionary time. Starting from the top, the Homo Naledi skull represents a fascinating study in evolutionary contradictions. The brain case itself is remarkably small, with an endocranial volume ranging from 465 to 610 cubic centimeters. To put this in perspective, that's smaller than the brain of some Australopithecines who lived 3 million years ago, and roughly equivalent to the brain size of a modern chimpanzee. Yet the overall shape and proportions of the skull are distinctly more human-like than those of much older hominins. The skull displays a well-developed supraorbital torus, the bony ridge above the eye sockets, that is reminiscent of Homo erectus specimens from nearly 2 million years ago. There's a pronounced occipital bun at the back of the skull, another feature typically associated with much earlier human species. Yet the face, while projecting, lacks the massive, robust characteristics of earlier hominins and instead shows a more gracile, human-like construction. Perhaps most remarkably, detailed analysis of the brain's surface impressions revealed neural organization patterns that were surprisingly modern. Despite its diminutive size, the Homo Naledi brain showed structural features similar to other Homo species rather than to Australopithecines or great apes. The frontal lobe displayed characteristics associated with more advanced cognitive abilities, including areas potentially related to language processing and social cognition. The contradiction extended to the brain's asymmetry patterns. Modern human brains show distinctive left-right asymmetries that are thought to be linked to language and other sophisticated cognitive functions. Homo Naledi brains displayed similar asymmetrical patterns, particularly in the frontal and temporal regions. This suggested that despite their small size, these brains might have been capable of more complex cognitive processing than their volume alone would suggest. Moving down to the postcranial skeleton, everything below the skull, the anatomical paradoxes became even more pronounced. The shoulder girdle of Homo Naledi was configured much like that of Australopithecines, with a shoulder blade shape and positioning that would have been ideal for climbing and suspensory behavior in trees. The clavicle showed features associated with overhead arm movement, and the overall shoulder anatomy suggested individuals who spent significant time with their arms raised above their heads. Yet attached to these primitive shoulders were arms and hands that told a completely different evolutionary story. The hand of Homo Naledi was remarkably human-like in its overall proportions and capabilities. The thumb was robust and long, with muscular attachments indicating a powerful precision grip. The wrist joint was configured almost identically to that of modern humans, allowing for the kind of complex rotational movements necessary for sophisticated tool manufacture and use. The finger bones, however, presented another contradiction. While the overall hand proportions were modern, the individual finger bones were distinctly curved, even more curved than those found in Australopithecus specimens. This curvature is typically associated with adaptations for grasping branches and climbing, suggesting that Homo naledi hands were designed for both precise manipulation and arboreal locomotion. The arms themselves showed a mixture of features. The humerus displayed relatively low torsion compared to modern humans, a characteristic shared with more primitive hominins and associated with climbing adaptations. Yet the overall arm proportions and muscle attachment sites suggested individuals capable of the kind of complex arm movements required for tool use and manipulation. The torso of Homo naledi continued the pattern of mixed features. The rib cage was relatively broad and flared, similar to that of Australopithecus afarensis and other early hominins. This body shape would have given Homo naledi a somewhat different appearance from modern humans, with a broader chest tapering to a narrower waist. The vertebral column, where preserved, showed proportions most similar to other Pleistocene members of the genus Homo, though the specimens were notably small. Perhaps most surprising was the pelvis. While Homo naledi was clearly a committed biped, there is no question they walked upright as their primary form of locomotion. Their pelvic anatomy retained many primitive characteristics. The iliac blades were more flared than in modern humans, similar to the configuration seen in Australopithecines. This would have given them wider hips relative to their body size and might have influenced their gait patterns. The contradiction between pelvic anatomy and locomotor behavior became even more apparent when researchers examined the lower limb bones. The femur showed clear adaptations for efficient bipedal locomotion, with muscle attachment sites and overall architecture indicating individuals capable of long-distance walking. The knee joint was fully adapted for upright walking, and the tibia displayed the kind of features associated with habitual bipedalism. The foot of Homo naledi was perhaps the most human-like part of their entire anatomy. The arch structure, toe proportions, and overall foot mechanics were virtually identical to those of modern humans. There was no question that these individuals walked with a fully upright, efficient gait that would have allowed them to cover long distances on the ground with minimal energy expenditure. Yet even the lower limb showed some primitive retentions. The proximal femur retained features associated with climbing adaptations, and some muscle attachment sites suggested individuals who were still spending significant time in non-bipedal postures. The overall picture was of individuals who were primarily terrestrial bipeds, but who retained significant capabilities for arboreal behavior. This anatomical mosaic raised profound questions about how Homo naledi actually lived and moved through their environment. Were they primarily ground-dwelling creatures who occasionally climbed trees, or were they still spending substantial amounts of time in arboreal settings? The anatomical evidence suggested they were capable of both terrestrial and arboreal locomotion with considerable skill. The body size of Homo naledi added another layer to the anatomical puzzle. At an estimated 143.6 centimeters tall and 39.7 kilograms in weight, they were notably smaller than most other Homo species, but larger than Australopithecines. This intermediate body size was consistent with their position between these groups in many other anatomical features. The small body size, combined with the small brain, resulted in an encephalization quotient, a measure of relative brain size, of only 4.5. This was lower than virtually all other Homo species and comparable to some Australopithecines. Yet the brain's internal organization suggested cognitive capabilities that might have exceeded what this simple ratio would predict. Sexual dimorphism in Homo naledi was relatively limited, more like that seen in modern humans than in earlier hominins, where males were often dramatically larger than females. This pattern suggested social structures that were less dominated by physical competition between males, possibly indicating more cooperative social arrangements. The overall anatomical pattern raised questions about evolutionary processes that traditional models had difficulty explaining. How could a species retain such primitive features while simultaneously evolving others to advanced states? What selective pressures could have maintained this particular combination of characteristics for hundreds of thousands of years? Some researchers suggested that Homo naledi represented a mosaic, evolutionary pattern where different body parts evolved at different rates in response to different environmental pressures. The hands evolved for tool use, the feet for efficient bipedalism, but the shoulders and climbing adaptations were retained because they remained useful for exploiting arboreal resources. Others proposed that Homo naledi might represent an example of evolutionary reversal, where some features became more primitive over time. This was a more controversial interpretation, as it required explaining why larger brains or more advanced body plans might have been disadvantageous under certain circumstances. The anatomical paradox of Homo naledi highlighted just how much scientists still didn't understand about the evolutionary forces that shaped human development. Here was a species that seemed to violate many of the simple rules that had been used to explain human evolution, yet had clearly been successful enough to persist for hundreds of thousands of years in one of the most competitive environments on Earth. Chapter 7. Tool capabilities. One of the most intriguing mysteries surrounding Homo naledi concerns their relationship with stone tools. Despite having hands that appear perfectly designed for sophisticated tool manufacture and use, not a single stone tool has been found in direct association with Homo naledi fossils in either the Dinaledi or Lesedi chambers of Rising Star Cave. This absence has sparked intense debate about the technological capabilities of these small-brained hominins. The hand anatomy of Homo naledi tells a compelling story about dexterity and manipulation. Their thumbs were robust and elongated, with powerful muscle attachments indicating a strong precision grip. The fingertips showed the broad, flat morphology associated with enhanced tactile sensitivity. The wrist joint was configured almost identically to that of modern humans, allowing for complex rotational movements and fine motor control. These anatomical features are virtually identical to those found in species that are known tool makers. The precision grip capabilities evidenced by Homo naledi hand bones would have allowed them to hold small objects firmly between thumb and fingers while maintaining precise control over hand movements. The wrist morphology would have permitted a kind of complex rotational motions necessary for napping stone tools or using them for various tasks. The metacarpals, the long bones in the palm of the hand, showed adaptations for both power and precision gripping. The muscle attachment sites indicated individuals capable of applying significant force when grasping objects, while the overall proportion suggested the fine motor control necessary for delicate manipulative tasks. This combination is exactly what you would expect to see in a species that manufactured and used sophisticated tools. Yet the archaeological record from the Rising Star Caves tells a different story. Despite intensive excavation and careful screening of sediments, researchers have found no stone tools in the chambers where Homo naledi remains were discovered. This absence is particularly puzzling given that the caves have preserved organic materials and small bone fragments that would have been far more likely to disappear than durable stone artifacts. The lack of tools in the cave chambers doesn't necessarily mean that Homo naledi didn't make or use stone tools. After all, the caves appear to have been used for mortuary purposes rather than as living sites. The absence of tools might simply reflect the fact that these weren't places where daily activities, including tool use, took place. This interpretation gained support from the broader archaeological context of southern Africa during the Middle Pleistocene. The region has yielded extensive stone tool assemblages from this time period, including sophisticated early Stone Age, Acheulean, and Middle Stone Age industries. These tool traditions demonstrate complex manufacturing techniques, standardized forms, and evidence for planning and foresight in their production. If Homo Naledi wasn't responsible for these tool industries, then who was? The fossil record from southern Africa during this period is surprisingly sparse. Apart from Homo Naledi, very few other hominin fossils have been found that could be associated with the rich archaeological record. This has led some researchers to suggest that Homo Naledi might indeed have been the makers of at least some of these stone tool traditions. The possibility that Homo Naledi manufactured stone tools is both exciting and problematic. Their hand anatomy certainly suggests they had the necessary physical capabilities. Their brain anatomy, while small, showed organizational patterns that might have supported the cognitive demands of tool manufacture. And they were the only clearly identified hominin species in the region during much of the relevant time period. But attributing sophisticated stone tool industries to a species with such a small brain challenges conventional assumptions about the relationship between brain size and technological capability. The Acheulean tradition, for example, involves the production of large symmetrical hand axes that require considerable planning, skill, and understanding of stone fracture mechanics. Could a species with a brain only 1/3 the size of ours really have mastered such complex technologies? Some researchers have suggested that the cognitive demands of stone tool manufacture might not be as great as traditionally assumed. Modern experimental studies have shown that many aspects of stone knapping can be learned through simple imitation and practice, without requiring the kind of abstract thinking that large brains are thought to enable. Perhaps Homo Naledi was capable of sophisticated tool manufacture through different cognitive pathways than those used by larger brain species. The curved finger bones of Homo Naledi add another dimension to the tool use question. While these features are typically interpreted as climbing adaptations, they might also have provided advantages for certain types of tool use. The enhanced grip strength that curved fingers would have provided could have been beneficial for tasks requiring sustained gripping of heavy tools or for activities like digging. Recent studies of tool use in other species have revealed that sophisticated technology doesn't always require large brains. Chimpanzees, with brains roughly the same size as Homo Naledi, manufacture and use a variety of tools including termite, fishing sticks, stone hammers for nut cracking, and spears for hunting small mammals. While these tools are simpler than human stone industries, they demonstrate that significant technological behavior is possible with relatively small brains. The absence of tools in the rising star caves might also reflect preservation biases or sampling issues. Stone tools could have been present originally, but removed by later geological processes, or they might be located in areas of the caves that haven't been excavated yet. The discovery of what appeared to be a stone tool near one of the Homo Naledi hands in recent excavations suggest that such artifacts might indeed be present but rare. Another possibility is that Homo Naledi relied more heavily on organic tools that wouldn't preserve in the archaeological record. Many modern hunter-gatherer societies use primarily wooden, plant fiber, or other perishable tools, with stone implements forming only a small part of their toolkit. If Homo Naledi followed a similar pattern, their technological capabilities might be virtually invisible in the fossil record. The sophisticated hand anatomy of Homo Naledi also raises questions about what other manual activities they might have engaged in beyond stone tool manufacture. Their precision grip capabilities would have been useful for plant food processing, weaving or braiding plant fibers, manipulating wooden implements, or even for complex social behaviors like grooming. The apparent contradiction between sophisticated hand anatomy and the absence of associated stone tools highlights one of the central challenges in interpreting the Homo Naledi fossil record. Time and again, these fossils seem to suggest capabilities that exceed what their small brain size would predict. Yet direct evidence for these capabilities remains elusive. Some researchers have proposed that Homo naledi might represent an example of mosaic evolution in technological behavior, where some aspects of tool-related anatomy evolved while others, such as the cognitive capacity for complex tool manufacture, remained relatively primitive. This would suggest that the relationship between anatomy and behavior is more complex than simple correlations would indicate. Others have suggested that the tool-making capabilities evidenced by Homo naledi's anatomy might have been used for purposes other than stone tool manufacture. Perhaps their sophisticated manual dexterity was primarily adapted for complex plant food processing, intricate nest-building behaviors, or other activities that required fine motor control but didn't involve stone knapping. The question of Homo naledi tool capabilities remains one of the most important unresolved issues in understanding this species. Their hand anatomy clearly indicates sophisticated manipulative abilities, but the archaeological context provides limited direct evidence for how these abilities were actually used. As excavations continue and new analytical techniques are developed, researchers hope to gain clearer insights into the technological world of these enigmatic hominins. What seems certain is that Homo naledi possessed the anatomical prerequisites for complex tool manufacture and use. Whether they actually engaged in such behaviors, and to what extent, remains one of the most intriguing questions surrounding this remarkable species. Chapter 8. Fire Controversy in late 2022. Lee Berger made an announcement that sent shockwaves through the paleoanthropologic community. His team had discovered evidence that Homo naledi might have controlled fire deep within the Rising Star cave system. If true, this discovery would represent some of the earliest evidence for deliberate fire use by any hominin species, and the first such evidence attributed to a small-brained human ancestor. The implications were staggering. Fire control has long been considered one of the hallmarks of advanced human cognition, requiring planning, maintenance, and understanding of complex cause and effect relationships. The idea that Homo naledi, with brains only slightly larger than chimpanzees, might have mastered fire challenged fundamental assumptions about the cognitive requirements for this crucial technological breakthrough. Berger's announcement described multiple lines of evidence for fire use throughout the Rising Star cave system. In August 2022, while examining underground chambers where Homo naledi fossils had been found, Berger reported finding blackened, burned areas on cave ceilings and walls. Some surfaces showed what appeared to be soot particles, and certain areas displayed the kind of heat discoloration that results from prolonged exposure to flames. The research team, led by expedition co-director Canelo Malapiane, had uncovered what they interpreted as small fireplaces containing charred wood fragments and burned bones of antelopes and other animals. Perhaps most significantly, similar evidence was found in the remote chambers where Homo naledi fossils had been discovered, suggesting a direct connection between fire use and the presence of these hominins. We have massive evidence. It's everywhere. Huge lumps of charcoal, thousands of burned bones, giant hearths and baked clay, Berger announced during a lecture at the Carnegie Institution of Science. The team claimed to have found evidence of hearths, soot-stained cave walls, and extensive charcoal deposits throughout the cave system. The discovery seemed to provide a crucial, missing piece of the Homo naledi puzzle. If these small-brained hominins were indeed placing bodies in the deep, dark chambers of Rising Star Cave, they would have needed some form of artificial light to navigate the treacherous passages and carry out their mortuary activities. Fire would have been the obvious solution, providing both illumination and potentially serving other purposes such as cooking or protection. Idea that Homo naledi used fire also helped explain some of the logistical challenges involved in their proposed mortuary behavior, carrying bodies through the narrow, Winding passages to reach the burial chambers would have been difficult enough with modern lighting equipment. Without artificial illumination, such activities would have been virtually impossible. Fire torches could have provided the light necessary for these complex underground expeditions. The potential antiquity of fire use by Homo Naledi was particularly significant, with dates ranging from 335,000 to 236,000 years ago. Any fire used by this species would represent some of the earliest evidence for controlled fire in Africa. Previous evidence for early fire use was scattered and often controversial, with clear evidence for habitual fire control generally not appearing until much later in the archaeological record. However, the fire claims immediately faced intense scrutiny from the scientific community. Critics pointed out several fundamental problems with the evidence and its interpretation. First and most importantly, none of the supposed fire evidence had been properly dated. Without determining the age of the charcoal and burned materials, there was no way to establish whether they were contemporary with Homo Naledi or resulted from much more recent activities. Professor Andy Harries from La Trobe University was among the skeptics. There is no evidence that Homo Naledi lit fires in the cave. Purported burning locations could just be from manganese staining, and charcoal within the cave remains to be dated. Charcoal from natural fires is not uncommon in caves. This criticism highlighted a crucial point. Caves are environments where charcoal and fire evidence can accumulate from many different sources over long periods of time. Natural wildfires can drive charcoal and ash into cave systems, where they may be preserved for thousands of years. More recent human activities, including modern cavers using torches or fires, could also account for burned materials found in the caves. The lack of proper scientific analysis was another major concern. No definitive evidence had been presented to demonstrate that the supposed hearths were actually in situ burning features, rather than accumulations of charcoal from other sources. Techniques such as micromorphology, soil chemistry analysis, and magnetism studies, standard approaches for identifying ancient fire use, had not been applied to confirm the nature of the burned materials. Some researchers also questioned whether the supposed soot stains and heat discoloration on cave walls were actually evidence of fire use at all. Similar markings can result from natural processes, including water staining, mineral deposits, or even the gradual accumulation of organic materials over time. Without careful chemical analysis, it's often impossible to distinguish between genuine fire evidence and these natural phenomena. The controversy was further complicated by the broader debate surrounding Homo Naledi's behavioral capabilities. Many researchers remain skeptical that a species with such a small brain could master fire control, which requires not just the ability to create fire, but also to maintain it, transport it, and understand its properties well enough to use it safely in enclosed spaces. Fire control involves numerous complex cognitive processes, understanding combustible materials, predicting fire behavior, planning for fuel needs, coordinating group activities around fire maintenance, and understanding safety protocols to prevent accidents. These capabilities have traditionally been associated with larger brain species and more recent time periods in human evolution. Critics also pointed out that the supposed fire evidence had been announced through media presentations rather than peer-reviewed scientific publications. This approach raised concerns about the quality of the evidence and the thoroughness of the analysis. Major claims about human evolution typically require extensive peer review and independent verification before being accepted by the scientific community. The geographic distribution of the supposed fire evidence also raised questions. If Homo Naledi was indeed using fire throughout the Rising Star cave system, Researchers would expect to find similar evidence at other sites where this species lived. Yet no fire evidence has been reported from other Homo naledi sites or from other locations where small-brained hominins have been found. Some researchers suggested alternative explanations for the accumulation of burned materials in the caves. Natural wildfires are common in the South African landscape, and smoke and charcoal from surface fires could have been drawn into the cave system by air currents. More recent human activities, including use of the caves by modern people or even by other hominin species, could also account for fire evidence without requiring that Homo naledi itself controlled fire. The timing of the fire claims also raise questions. The supposed evidence was announced several years after the initial discovery and analysis of Homo naledi fossils, leading some to wonder why such important evidence hadn't been reported earlier. This timing, combined with the media-focused announcement strategy, led some critics to suggest that the fire claims might be more about generating publicity than advancing scientific understanding. Despite the controversies, some researchers remained open to the possibility that Homo naledi might have used fire. The anatomical evidence for sophisticated hand dexterity and the behavioral evidence for complex mortuary practices suggested that these hominins were capable of more advanced behaviors than their small brain size might predict. If they could navigate complex cave systems and engage in mortuary behavior, perhaps fire control wasn't beyond their capabilities. The debate over Homo naledi fire use highlighted broader questions about the relationship between brain size and behavioral complexity. Traditional models had assumed that fire control required the cognitive capabilities associated with larger brains. But perhaps these assumptions needed to be reconsidered in light of new evidence. As the controversy continued, researchers called for more rigorous scientific analysis of the supposed fire evidence. Proper dating, chemical analysis, and comparison with known fire sites would be necessary to establish whether Homo naledi actually controlled fire or whether the evidence resulted from other processes. The fire controversy remained unresolved, but it had already succeeded in challenging assumptions about early human capabilities and raising important questions about the relationship between brain size and technological achievement. Whether or not Homo naledi actually used fire, the debate had opened new avenues for thinking about the cognitive abilities of our small-brained ancestors. Chapter 9. Social Behavior. Evidence emerging from the Rising Star cave system suggests that Homo naledi engaged in remarkably complex social behaviors that would have required sophisticated group coordination, cultural transmission of knowledge, and perhaps even forms of symbolic thinking. If the interpretations of deliberate body placement are correct, these small-brained hominins were capable of social behaviors that scientists had previously attributed only to much larger brain species. The mortuary behavior itself provides the clearest window into Homo naledi social complexity. The repeated placement of bodies in extremely inaccessible cave chambers would have required coordinated group efforts involving multiple individuals working together toward a common goal. This wasn't something that could have been accomplished by a single individual. It would have demanded social cooperation on a scale that implies sophisticated communication and shared cultural practices. Consider the logistics involved in transporting a body through the treacherous passages of Rising Star Cave. The journey to the Naledi chamber requires navigating through spaces barely wide enough for a single person, descending vertical shafts, and squeezing through openings that challenge even experienced modern cavers. Carrying a deceased individual through this obstacle course would have required careful planning, precise coordination, and probably involved multiple people working in sequence to pass the body through different sections of the cave. This kind of coordinated effort suggests that Homo naledi groups possessed what researchers call shared intentionality. the ability for multiple individuals to work together toward a common goal while understanding their individual roles in the larger effort. This cognitive capacity has been identified as one of the key differences between human and non-human social cognition. Yet the evidence suggests that even small-brained Homo Naledi possess some version of this ability. The repeated nature of the mortuary behavior adds another layer of social complexity. The presence of individuals from different age groups in both the Naledi and Naledi chambers suggests that body placement occurred multiple times over extended periods. This pattern implies cultural transmission of knowledge about mortuary practices from one generation to the next. Young Homo Naledi individuals would have had to learn not just where the burial chambers were located, but also how to navigate the complex cave system and carry out the physically demanding task of body transport. Cultural transmission of this complexity would have required sophisticated communication abilities. Even if Homo Naledi didn't possess language in the modern human sense, they would have needed some way to convey detailed spatial information about cave navigation, coordinate complex group activities, and maintain cultural continuity across generations. The areas of the Homo Naledi brain associated with communication and social cognition showed surprisingly human-like development, suggesting they might have possessed more advanced communication abilities than their overall brain size would predict. The social implications of mortuary behavior extend beyond the practical challenges of body transport. The decision to invest significant time and energy in disposing of the dead, with no apparent immediate benefit to the living, suggests that Homo Naledi possessed what researchers call deferred gratification, the ability to engage in costly behaviors based on abstract motivations rather than immediate needs. This capacity for deferred gratification has important implications for understanding Homo Naledi's social structure. Groups that can coordinate costly activities based on shared cultural values are likely to have more complex social relationships than those focused purely on immediate survival needs. The mortuary behavior suggests that Homo Naledi groups might have possessed shared belief systems or cultural practices that transcended individual self-interest. The age structure of the individuals found in the caves provides additional insights into Homo Naledi's social organization. The presence of infants, juveniles, adults, and elderly individuals suggests that all members of the group receive similar treatment in death, regardless of age or presumably social status. This pattern is more consistent with egalitarian social structures than with highly hierarchical systems where only certain individuals would receive elaborate mortuary treatment. The apparent lack of sexual dimorphism in Homo Naledi also supports the interpretation of relatively egalitarian social structures. In many primate species, high levels of sexual dimorphism are associated with intense male-male competition and polygynous mating systems where dominant males control access to multiple females. The relatively similar body sizes of male and female Homo Naledi suggest that their social systems might have been less dominated by physical competition between males. Some researchers have suggested that the mortuary behavior itself provides evidence for emotional attachments between Homo Naledi individuals. The investment of significant effort in treating the dead with apparent care suggests that these hominins form strong social bonds with group members and experienced grief or other emotions related to death. This interpretation implies that Homo Naledi possessed the emotional and cognitive capacity for empathy and social attachment. The coordination required for mortuary activities also suggests that Homo Naledi groups possessed some form of leadership or decision-making structure. Someone would have had to initiate the mortuary activities, coordinate the logistics of body transport, and ensure that the cultural knowledge necessary for these practices was transmitted to new generations. This implies social structures more complex than simple dominance hierarchies based on physical strength or aggression. The geographic distribution of Homo naledi remains also provides clues about their social organization. The concentration of fossils in specific chambers of the rising star cave system, rather than being scattered across the landscape, suggests that these groups maintained strong territorial attachments to particular locations. This pattern implies that Homo naledi groups had detailed knowledge of their local environment and maintained cultural connections to specific geographic areas across multiple generations. The sophisticated hand anatomy of Homo naledi, while not directly social evidence, has implications for understanding their cultural capabilities. The precision grip and fine motor control, evidenced by their hand bones, would have enabled complex manipulative behaviors that could have supported various cultural activities, from tool manufacture to plant processing to possibly even early forms of art or symbolic expression. Recent research on Homo naledi brain organization has revealed neural features that might have supported complex social cognition. Despite their small overall brain size, Homo naledi showed human-like development in brain regions associated with social emotions, empathy, and possibly even language processing. These neural features suggest that their social capabilities might have exceeded what simple brain size measurements would predict. The social behavior of Homo naledi also raises questions about their interactions with contemporary human species. Given that they lived alongside early Homo sapiens and possibly other hominin species, researchers have wondered whether there might have been contact between different human groups. The distinctive mortuary practices of Homo naledi suggest that they maintained cultural traditions that were uniquely their own. But whether these developed in isolation or through interaction with other species remains unknown. Some researchers have speculated that the social complexity evidenced by Homo naledi might help explain their long-term evolutionary success. While their small brains might have put them at a disadvantage in direct competition with larger-brained species, their sophisticated social cooperation might have allowed them to exploit ecological niches that were unavailable to less socially organized groups. The evidence for complex social behavior in Homo naledi has broader implications for understanding the evolution of human sociality. Traditional models had assumed that sophisticated social cooperation required the large brains and advanced cognitive abilities of modern humans. The Homo naledi evidence suggests that complex social behaviors might have evolved much earlier in human evolution and might not require the massive neural infrastructure that scientists had previously thought necessary. As research continues, the social behavior of Homo naledi remains one of the most intriguing aspects of this remarkable species. Their apparent capacity for complex group coordination, cultural transmission, and possibly even symbolic behavior challenges our understanding of what it means to be social and suggests that the roots of human social complexity might extend much deeper into our evolutionary past than previously imagined. Chapter 10. Burial Evidence: The Interpretation of Deliberate Burial by Homo naledi represents one of the most controversial and potentially revolutionary claims in modern paleoanthropology. If confirmed, it would demonstrate that complex mortuary behaviors, previously thought to be unique to large-brained humans like Neanderthals and modern Homo sapiens, were actually practiced by a small-brained species hundreds of thousands of years ago. The evidence for deliberate burial comes from multiple discoveries within the rising star cave system, but the most compelling evidence was announced in 2023 with the description of what researchers interpreted as formal burial sites within the cave chambers. According to the research team led by Lee Berger, they had identified at least 3 separate burial features, 2 in the Naledi chamber and 1 in a newly explored area called the Hill Antechamber. The most detailed evidence came from the Hill Antechamber, where researchers reported finding what appeared to be a deliberately excavated pit containing the remains of at least 1 adult individual. The body was said to be lying in a flexed position within the depression, covered with sediments that appeared to have been intentionally placed rather than naturally accumulated. Near the remains, the team reported finding a stone tool that they suggested might have been deliberately placed with the body in the Naledi chamber. Researchers identified 2 additional features they interpreted as burial sites. These involved concentrations of skeletal remains in what appeared to be shallow depressions in the cave floor. The bones showed patterns of articulation and positioning that the research team argued were consistent with bodies having been deliberately placed and covered with sediments shortly after death. The burial interpretation was based on several lines of evidence. First, the spatial distribution of bones within the supposed burial features showed patterns that differed from natural accumulations, rather than the random scattering typical of bones that have been disturbed by water, gravity, or animal activity. The remains showed organization that suggested deliberate placement. Second, some skeletal elements were found in anatomical articulation, indicating that they had been buried while soft tissues were still holding the bones together. This pattern is consistent with relatively rapid burial after death, which would require intentional action rather than gradual accumulation over time. Third, the sediments surrounding the remains showed characteristics that the research team interpreted as evidence of deliberate infilling, rather than the gradual accumulation of sediments through natural processes. The deposits appeared to represent rapid burial events where material was intentionally placed over the bodies. The research team also pointed to the absence of evidence for natural accumulation processes. They found no indication that water flow, gravitational movement, or animal activity could account for the specific positioning and preservation of the remains. This absence of natural explanations, they argued, supported the interpretation of deliberate human action. However, the burial claims faced immediate and intense criticism from other researchers. The critique, published in the Journal of Human Evolution, argued that the evidence presented was insufficient to support claims of deliberate burial, and that the research team had not adequately applied the rigorous methodological standards typically required for such interpretations. Critics pointed out that identifying deliberate burial in the archaeological record requires meeting very specific criteria that have been developed through decades of research on known burial sites. These criteria include clear evidence for deliberate excavation of burial pits, unambiguous positioning of bodies in specific postures, evidence for rapid covering of remains, and absence of natural processes that could account for the observed patterns. Professor Michael Petraglia from Griffith University was among the critics. Unfortunately, there is a distinct possibility that the so-called stone artifact next to the hominin hand is a geofact, and not a product of stone tool flaking by Homo Naledi. This criticism highlighted concerns that what appeared to be deliberately placed artifacts might actually be naturally formed stones that coincidentally resemble tools. The sedimentological evidence also came under scrutiny. Critics argued that the research team had not conducted the detailed micromorphological and geochemical analyses necessary to distinguish between natural sediment accumulation and deliberate burial. Cave environments are particularly complex, with sediments accumulating through various natural processes that can create patterns resembling human activity. The absence of clear pit outlines was another major concern. In most confirmed archaeological burials, excavation reveals clear evidence for the original burial pit, a distinct feature cut into underlying sediments where the body was placed. The Rising Star burial claims lacked this fundamental evidence, instead relying on more ambiguous patterns of bone distribution and sediment characteristics. Some researchers also questioned the statistical analysis used to support the burial interpretation. They argued that the spatial patterns of bones could be explained by natural processes and that the research team had not adequately tested alternative hypotheses for bone accumulation. The controversy was intensified by concerns about the publication process. The burial claims were initially announced through preprint publications and media presentations before undergoing full peer review. This approach drew criticism from researchers who argued that such extraordinary claims required the most rigorous scientific scrutiny before being presented to the public. Dr. Maria Martín Torres from the National Research Center on Human Evolution in Spain was among those calling for more rigorous analysis. There is no convincing scientific evidence to indicate that H. Naledi buried their dead based on the information thus far presented. The investigators have not employed the wide range of scientific methods designed to answer the questions posed. The scientific community's response highlighted the methodological challenges involved in identifying deliberate burial in the fossil record. Unlike stone tools, which bear clear evidence of intentional manufacture, burial evidence is often more ambiguous and requires careful analysis to distinguish human agency from natural processes. Despite the criticisms, some researchers remained open to the possibility that Homo Naledi engaged in mortuary behavior, even if the specific evidence for formal burial was questionable. The repeated accumulation of bodies in extremely inaccessible cave chambers was difficult to explain through natural processes alone. Regardless of whether formal burial pits were involved, the broader context of Homo Naledi discoveries also provided some support for complex mortuary behavior. The presence of remains in two separate, equally inaccessible chambers of the cave system suggested some form of repeated, intentional body placement. The age distribution of individuals, ranging from infants to elderly adults, was consistent with ongoing mortuary practices rather than single catastrophic events. Some researchers proposed alternative interpretations that might bridge the gap between the burial claims and the criticisms. Perhaps Homo Naledi engaged in simple body placement or disposal without the more elaborate burial practices, involving formal pit excavation and deliberate positioning. This interpretation would still represent sophisticated mortuary behavior while avoiding some of the more controversial aspects of the burial claims. The debate over Homo Naledi burial evidence reflected deeper tensions in paleoanthropology about what kinds of behaviors could be attributed to small-brained hominins. Traditional models had assumed that complex mortuary practices required the advanced cognitive abilities associated with larger brains. But the anatomical and behavioral evidence from Homo Naledi was challenging these assumptions. The controversy also highlighted the importance of applying rigorous methodological standards to extraordinary claims. The suggestion that a species with a brain one-third the size of modern humans was engaging in deliberate burial required exceptional evidence, and critics argued that such evidence had not yet been provided. As the debate continued, researchers called for additional analysis using established archaeological methods for identifying burial. Detailed micromorphological analysis of sediments, geochemical studies to identify human impact on cave deposits, and more extensive excavation to search for clear pit outlines were among the suggested approaches. The burial controversy raised important questions about the cognitive and cultural capabilities of early human species. If Homo Naledi was indeed engaging in deliberate mortuary behavior, it would suggest that the roots of human symbolic and cultural behavior extended much deeper into our evolutionary past than previously thought. Whether or not the specific claims for formal burial are ultimately confirmed, the Homo Naledi discoveries had already demonstrated that these small-brained hominins were capable of remarkably complex behaviors. the repeated transport of bodies into inaccessible cave chambers, regardless of whether formal burial was involved, represented a level of behavioral sophistication that challenged conventional understanding of early human capabilities. The ongoing research and debate around Homo Naledi burial evidence highlighted how much scientists still had to learn about the behavioral evolution of early human species. Each new discovery seemed to reveal greater complexity and sophistication among our small-brained ancestors than anyone had previously imagined. Chapter 11. Rock art, perhaps the most controversial claim surrounding Homo Naledi, involves the discovery of what researchers interpret as deliberately created rock engravings deep within the rising star cave system. If confirmed, these markings would represent the earliest known rock art in the archaeological record, predating previously known examples by tens of thousands of years and attributed to a species with a brain roughly one-third the size of modern humans. The supposed engravings were discovered in passages and chambers throughout the rising star cave system, but the most significant examples were found near areas where Homo Naledi fossils had been recovered. The markings consist of geometric patterns carved into the cave walls, including cross-hatched lines, squares, triangles, and what appeared to be deliberately arranged intersecting marks forming complex designs. According to Lee Berger and his research team, these engravings show clear evidence of intentional creation. The marks appear to have been made by abrading or scraping the cave wall surface, creating grooves that penetrate through natural surface layers to expose fresh rock beneath. The research team argued that the depth, consistency, and patterning of these marks could not be explained by natural weathering processes or accidental damage. The most compelling examples, according to the researchers, show sophisticated geometric organization. Some engravings consist of parallel lines arranged in cross-hatched patterns, while others show what appear to be deliberate attempts to create recognizable shapes like squares and triangles. The surfaces bearing these engravings appeared to have been prepared and smoothed before the markings were made, suggesting a deliberate artistic process. The research team also reported finding what they interpreted as a stone tool near one of the engraved surfaces, close to the hand of a Homo Naledi individual. They suggested that this tool might have been used to create the engravings, providing a direct link between the markings and the hominin remains. The tool showed what appeared to be use-wear patterns consistent with scraping or abrading activities. If these interpretations are correct, the implications would be revolutionary. Rock art has traditionally been considered one of the hallmarks of modern human cognition, requiring abstract thinking, symbolic representation, and the ability to create meaningful visual communications. The earliest confirmed rock art in Africa dates to around 75,000 years ago, associated with anatomically modern humans and much larger-brained species. The attribution of rock art to Homo Naledi would push back the origins of symbolic behavior by more than 150,000 years and demonstrate that even small-brained hominins were capable of abstract symbolic expression. This would fundamentally challenge assumptions about the cognitive requirements for artistic behavior and suggest that the capacity for symbolic thinking evolved much earlier in human evolution than previously thought. However, the rock art claims faced intense skepticism from the scientific community. Critics raised numerous concerns about the evidence and its interpretation, arguing that the research team had not adequately demonstrated that the markings were human-made rather than natural formations. Dr. Diego Garatti, a specialist in Paleolithic art, was among the skeptics. Detailed analyses are also needed to demonstrate that the so-called engravings are indeed human-made marks, as marks like these can be produced as a product of natural weathering or animal claws. This criticism highlighted a fundamental challenge in interpreting potential rock art, distinguishing between intentional human markings and the many natural processes that can create linear marks on cave walls. Water flow, mineral crystallization, thermal expansion and contraction, root growth, and animal activity can all create patterns that may superficially resemble deliberate engravings. The geological context of the rising star caves added to the skepticism. The caves are formed in Malmani dolomite, a type of limestone that is particularly prone to natural weathering patterns. Critics pointed out that numerous examples of shallow, cross-hatched erosional lines could be found throughout the Malmani dolomite formation, not just in areas associated with Homo Naledi remains. The lack of comparative analysis was another major concern. The research team had not systematically compared the supposed engravings with known examples of natural weathering patterns in similar geological contexts. Without such comparisons, it was difficult to determine whether the markings showed characteristics that would distinguish them from natural formations. Critics also questioned the dating of the engravings. Unlike organic materials that can be radiocarbon dated, rock engravings themselves cannot be directly dated unless they contain organic materials or are covered by datable deposits. The research team had not provided definitive evidence that the engravings were contemporary with Homo Naledi rather than much more recent creations. The possibility that the markings were created by more recent humans was particularly problematic. The rising star cave system had been known to cavers since the 1960s, and humans had been visiting South African caves for thousands of years. Without proper dating, there was no way to rule out the possibility that the engravings were created by anatomically modern humans at some point in the recent past. Some researchers also questioned the supposed tool associated with the engravings. Critics argued that what appeared to be a deliberately manufactured stone tool might actually be a geofact, a naturally broken stone that coincidentally resembled an artifact. Distinguishing between intentionally manufactured tools and naturally broken stones requires careful analysis of fracture patterns and edge characteristics that had not been adequately demonstrated. The pattern recognition issues raised additional concerns. Humans have a strong tendency to perceive intentional patterns in random markings, a psychological phenomenon known as pareidolia. Critics suggested that the research team might be seeing deliberate designs in what were actually random natural markings, especially given the extraordinary nature of the claims being made. The scientific community's response to the rock art claims was overwhelmingly skeptical. A comprehensive critique published in the Journal of Human Evolution argued that the evidence presented was insufficient to support claims of deliberate rock art creation by Homo Naledi. The critics called for much more rigorous analysis using established methods for authenticating ancient rock art. The controversy highlighted the methodological challenges involved in identifying the earliest examples of symbolic behavior in the archaeological record. Rock art authentication typically requires multiple lines of evidence, including detailed analysis of manufacturing techniques, comparison with natural weathering patterns, assessment of geological context, and whenever possible, direct or indirect dating of the markings. Some researchers suggested that the rock art claims reflected broader issues with the rising star research project's approach to extraordinary claims. They argued that the team had a pattern of announcing revolutionary discoveries through media presentations before subjecting them to adequate peer review and scientific scrutiny. The debate over the supposed Homo Naledi rock art also reflected deeper questions about the cognitive capabilities of small-brained hominins. Even researchers who were skeptical of the specific engravings acknowledged that the broader evidence for complex behavior by Homo Naledi was challenging traditional assumptions about the relationship between brain size and cognitive ability. If future research were to confirm that Homo Naledi created rock art, it would represent one of the most significant discoveries in the study of human cognitive evolution. However, the extraordinary nature of such a claim would require extraordinary evidence, and most researchers agreed that such evidence had not yet been provided. The rock art controversy remained unresolved, but it had already succeeded in raising important questions about early human symbolic capabilities and the methods used to identify the earliest evidence for human artistic expression. Whether or not Homo Naledi actually created rock art, the debate had highlighted how much scientists still had to learn about the cognitive and cultural evolution of our early ancestors. Chapter 12. Environmental Context. Understanding how Homo Naledi lived requires reconstructing the environmental conditions they encountered in southern Africa between 335,000 and 236,000 years ago. This was a period of significant climate change and environmental variability that would have presented both challenges and opportunities for early human populations across the continent. During the Middle Pleistocene, southern Africa experienced a complex pattern of climate fluctuations driven by global ice age cycles and regional weather systems. The period when Homo Naledi lived corresponded to parts of marine isotope stages 9, 8, and 7, intervals characterized by alternating glacial and interglacial conditions that dramatically affected rainfall patterns, vegetation communities, and animal populations across the region. The cradle of humankind region where Homo Naledi fossils were found would have experienced a climate somewhat different from today's conditions. During glacial periods, the area was generally cooler and drier than at present, with reduced rainfall and expanded grassland environments. During interglacial periods, conditions were warmer and wetter, supporting more extensive woodland and forest communities. These climate cycles would have created a dynamic, ever-changing landscape that required considerable adaptability from hominin populations. The shift between grassland and woodland environments would have affected the availability of different food resources, shelter opportunities, and water sources. Groups that could successfully adapt to these changing conditions would have had significant survival advantages. The vegetation of the region during Homo Naledi's time would have been a complex mosaic of different plant communities responding to local topography, soil conditions, and microclimatic variations. River valleys and protected areas might have supported gallery forests and dense woodland, while exposed uplands were dominated by grasslands and scattered trees. This environmental heterogeneity would have provided diverse opportunities for foraging and resource exploitation. Plant foods that formed the foundation of Homo Naledi's diet underground. Storage organs like tubers and roots would have been particularly important during periods of environmental stress. These foods provided reliable, high-energy resources that could be stored in the ground through seasonal dry periods and accessed when other food sources were scarce. The ability to efficiently exploit these resources might have been crucial for Homo Naledi's long-term survival in a variable environment. The seasonal patterns of plant growth and reproduction would have required detailed ecological knowledge from Homo Naledi groups. Underground storage organs are typically most nutritious and largest at specific times of year, often during or just after the growing season when plants have accumulated maximum energy reserves. Successfully exploiting these resources would have required understanding these seasonal cycles and planning group movements accordingly. Water availability would have been another critical factor shaping Homo Naledi behavior and distribution. During dry periods, access to reliable water sources would have been essential for survival. The cave systems where Homo naledi remains were found might have provided access to underground water sources or served as storage areas for water during dry seasons. Animal communities of Middle Pleistocene Southern Africa were dramatically different from those of today. Large mammal species that are now extinct roamed the landscape, including giant versions of modern species and entirely different evolutionary lineages. These animals would have presented both opportunities and challenges for early human populations. Large herbivores like ancient elephants, giant buffalo, and various antelope species would have provided potential sources of meat through hunting or scavenging. However, the landscape also included formidable predators, including large cats, hyenas, and other carnivores that would have posed serious threats to small-bodied hominins like Homo naledi. The presence of these large predators might help explain why Homo naledi used deep cave systems for mortuary purposes. Caves would have provided protection from scavengers that might otherwise have disturbed or destroyed bodies left on the surface. The deep, inaccessible chambers where Homo naledi remains were found would have been particularly secure from carnivore interference. The geological environment of the region also played important roles in Homo naledi ecology. The Malmani dolomite formations that characterized the cradle of humankind created extensive cave systems that could have served multiple functions for early human populations. Beyond their use for mortuary purposes, caves might have provided shelter, water storage, toolstone sources, and protection from predators and weather. The cave systems also created unique microenvironments that might have been particularly important during periods of environmental stress. Cave interiors maintain relatively constant temperatures and humidity levels, providing refuge from extreme weather conditions. Some caves might have supported specialized plant communities or provided access to underground water sources. The mineral-rich soils derived from dolomite weathering would have supported distinctive plant communities that might have been particularly important for Homo naledi subsistence. Many plants that produce large underground storage organs prefer well-drained, alkaline soils of the type found in dolomite regions. The concentration of Homo naledi remains in this particular geological setting might reflect their specialization in exploiting these specific plant communities. Fire ecology would have been another important environmental factor during Homo naledi's time. Lightning-sparked wildfires were natural features of the southern African landscape, creating complex mosaics of burned and unburned areas that supported different plant and animal communities. If Homo naledi controlled fire, they might have been able to participate in and modify these natural fire cycles for their own benefit. The environmental context also helps explain some aspects of Homo naledi's anatomy and behavior. Their relatively small body size would have been advantageous in environments where food resources were limited or unpredictable. Smaller bodies require fewer calories to maintain, allowing populations to survive on lower quality or more dispersed food sources. The retention of climbing adaptations in Homo naledi anatomy might have been particularly important in environments where vertical habitat diversity was significant. The ability to access tree-based resources, fruits, leaves, nesting sites, or escape routes from predators would have provided important survival advantages in woodland environments. The evidence for complex social behavior in Homo naledi might also reflect adaptations to challenging and variable environmental conditions. Cooperative groups would have been better able to monitor large territories for seasonal food resources, coordinate responses to environmental changes, and maintain the cultural knowledge necessary for survival in complex landscapes. The longevity of Homo naledi as a species, potentially persisting largely unchanged for hundreds of thousands of years, suggests that they developed successful strategies for coping with environmental variability, rather than evolving rapidly in response to changing conditions. They might have maintained flexible behavioral repertoires that allowed them to persist through multiple climate cycles. The environmental context of Homo naledi highlights the complex ecological challenges faced by Middle Pleistocene human populations in Africa. Success required not just anatomical adaptations, but also sophisticated behavioral flexibility, detailed ecological knowledge, and effective social cooperation. The evidence suggests that even small-brained species like Homo naledi were capable of developing remarkably sophisticated strategies for thriving in challenging and variable environments. Chapter 13. Brain Evolution. The brain of Homo naledi presents one of the most puzzling paradoxes in human evolution. With an endocranial volume of only 465 to 610 cubic centimeters, roughly equivalent to that of a chimpanzee, and smaller than most Australopithecines, it challenges every assumption scientists had made about the relationship between brain size and cognitive capability in human evolution. When researchers first began studying endocasts, internal molds of the brain cavity, from Homo naledi skulls, they expected to find a primitive brain organization consistent with the small overall size. Instead, they discovered something remarkable. Despite its diminutive size, the Homo naledi brain showed structural features that were surprisingly similar to those of much larger-brained human species. The frontal lobe organization was particularly striking. In modern humans, the frontal lobe is associated with complex cognitive functions, including planning, decision-making, social reasoning, and language processing. The Homo naledi brain showed frontal lobe patterns that were more similar to other Homo species than to Australopithecines or great apes, suggesting that important neural reorganization had occurred. Despite the lack of overall brain enlargement, one of the most intriguing discoveries was evidence for what appeared to be Broca's area, a brain region in modern humans that is crucial for language production. Researchers identified two grooves on Homo naledi endocasts that frame an area potentially corresponding to this language-related region. If confirmed, this would suggest that even small-brained hominins might have possessed some capacity for complex vocal communication. The brain asymmetry patterns in Homo naledi also showed human-like characteristics. Modern human brains display distinctive left-right asymmetries that are thought to be related to language processing and other advanced cognitive functions. Homo naledi brains showed similar asymmetrical patterns, particularly in the frontal and temporal regions, suggesting that the neural foundations for complex communication might have evolved much earlier than previously thought. The temporal lobe region, associated with memory and auditory processing, also showed human-like characteristics in Homo naledi. This area of the brain is crucial for the kind of complex spatial memory that would have been necessary for navigating the intricate cave systems where these hominins were found. The development of this brain region might help explain how Homo naledi was able to repeatedly find and use the deep cave chambers for mortuary purposes. Perhaps most surprisingly, the overall brain organization showed patterns that were more similar to other Homo species than to Australopithecines with comparable brain sizes. This suggested that neural reorganization, changes in how the brain was structured and organized, had been more important in early human evolution than simple brain enlargement. Quality of neural organization, rather than quantity of brain tissue, might have been the key factor in cognitive evolution. The encephalization quotient of Homo naledi, a measure of brain size relative to body size, was 4.5, which was lower than virtually all other Homo species, but comparable to some Australopithecines. However, the evidence for complex behaviors like mortuary practices and possible tool use, suggested that this simple ratio didn't capture the full picture of Homo Naledi's cognitive capabilities. Recent research has revealed that brain size alone is a poor predictor of cognitive ability across species. Factors like neural density, connectivity patterns, and regional organization can be much more important than overall volume. The Homo Naledi brain appeared to demonstrate this principle, showing that significant cognitive capabilities could be achieved with relatively modest neural resources if those resources were efficiently organized. The small brain size of Homo Naledi also raised important questions about the energetic costs of brain maintenance. Large brains are metabolically expensive, requiring about 20% of total daily energy expenditure in modern humans. The smaller brain of Homo Naledi would have had much lower energy requirements, potentially allowing these hominins to survive in environments where food resources were limited or unpredictable. This energetic consideration might help explain how Homo Naledi managed to persist for hundreds of thousands of years alongside larger brain species. While big brains might have provided certain cognitive advantages, they also came with substantial metabolic costs. In some environments or ecological niches, the energetic efficiency of smaller brains might have been more advantageous than the cognitive benefits of larger ones. The evidence for complex behavior in Homo Naledi forced researchers to reconsider fundamental assumptions about brain evolution in early humans. Traditional models had emphasized a linear progression from small-brained, cognitively simple ancestors to large-brained, behaviorally complex descendants. The Homo Naledi discoveries suggested that this progression was neither linear nor universal. Instead, the evidence pointed toward multiple evolutionary pathways in early human brain evolution. Some lineages, like the ancestors of modern humans and Neanderthals, pursued strategies involving brain enlargement and presumably enhanced cognitive capabilities. Others, like Homo Naledi, achieved behavioral complexity through neural reorganization without dramatic size increases. The coexistence of different brain evolution strategies raises questions about the selective pressures that drove early human cognitive development. If large brains were automatically advantageous, why did small brain species like Homo Naledi persist for so long? The answer might lie in the diversity of ecological niches and survival strategies available to early human populations. The Homo Naledi brain also provided insights into the evolution of specific cognitive capabilities. The evidence for mortuary behavior, complex navigation, and possibly tool use suggested that these abilities didn't require the massive neural infrastructure that scientists had previously assumed. Perhaps many advanced human behaviors could be achieved with more modest cognitive resources than traditional models suggested. Some researchers proposed that the key innovation in Homo Naledi brain evolution was not size increase, but rather the development of enhanced connectivity between different brain regions. Modern cognitive science has shown that intelligence depends heavily on how different parts of the brain communicate with each other. Even a small brain with efficient internal connections might be capable of surprising cognitive feats. The social implications of Homo Naledi brain organization were also significant. The evidence for complex group coordination required by mortuary behavior suggested that their brains were capable of sophisticated social cognition. The development of neural regions associated with empathy, cooperation, and communication might have been more important for their survival than overall brain enlargement. The language-related features potentially present in Homo Naledi brains raised particularly intriguing questions. If these small-brained hominins possessed some capacity for vocal communication, it would suggest that the foundations of human language evolved much earlier than previously thought. Even simple proto-language capabilities might have provided significant advantages for coordinating complex group activities. The study of Homo Naledi brain evolution also highlighted the importance of considering cognitive development in environmental context. The specific challenges faced by populations living in southern Africa during the Middle Pleistocene might have favored particular types of cognitive abilities over others. Brain evolution might have been shaped as much by local ecological pressures as by universal advantages of increased intelligence. The preservation of multiple, detailed endocasts from Homo Naledi provided researchers with an unprecedented opportunity to study brain evolution within a single species. The variation observed between individuals revealed insights into the range of neural organization patterns that were compatible with successful survival and reproduction. As research continues, the Homo Naledi brain remains one of the most important windows into understanding early human cognitive evolution. These small but complex brains demonstrated that the path to human intelligence was far more varied and creative than anyone had previously imagined, with multiple species experimenting with different solutions to the challenges of survival and reproduction in complex environments.